Um, our next speaker is Professor Hans-Jörg Vogel from the UFZ Helmholtz Centre for Environmental Research. We will talk about modeling water movement in soils under arid and semi-arid conditions. And
Yeah, good afternoon, everybody. I think it's obvious to everybody here in this round that soils are of critical importance for agriculture because they store the water and the nutrients which are just missing when water is short. Well, I don't want to be that bold to try to explain colleagues from Israel what are the critical issues when modeling water dynamics under dry conditions. But still, I think we can have a few areas of research where we can very nicely cooperate for the benefit of all of us. And I would like to make 2 or 3 points along these lines here. So what you see here in this image is an illustration that many scales are involved when we're talking about water in soils. So from the local root scale or the pore scale to the soil profiles up to the landscape. Well, the line you can see here just illustrates that whatever we are measuring in soil water relations, it depends on which scale we are looking. There are two critical scales, I guess. One is the scale of soil profile. This is the scale which is experienced by plants and which is important for agricultural management. And here the water fluxes are mainly vertical. This is why we can focus on the soil profile. Since the gradients are pointing either downwards or upwards, when it's dry, it's rather upwards. And here the critical question is, how does the irrigated or precipitation water is distributed in the soil? Is it stored for the usage of plants? Is it lost through surface runoff? Or it is flowing rapidly downwards below the root zones? That's critical for agricultural management. The other scale, which is important in other respect, is the landscape scale and the question, how are soils with different hydraulic properties distributed in the landscape? This is important for the question, how is the interactions between the land surface and the atmosphere? Where is surface runoff happening and where groundwater recharge? This depends on how the soils are distributed in the landscape. Also, the dynamics of the discharge of the surface waters, of course. Okay, so let's first jump on the scale of soil profiles and what the state of the art here. We do understand the physics of water in porous medium quite well, and we have to nice models describing water flow in soil, so we can describe infiltration very nicely, but there is always a but. This comes along with a number of assumptions which are not necessarily met when we look at infiltration in dry soils, for example. So one assumption is that we have a complete or at least constant wettability of internal surfaces. And this is especially critical when organic or soils with organic matter is drying out, or if we irrigate with wastewater, as we just heard from Aran Bengal. It's still 33% in Israel, and it's probably coming in Germany. And this water contain organic molecules which switch to hydrophobic when it's getting dry. And this produces quite strange phenomena in water dynamics. The other assumption is that water content and capillary forces are always nicely in equilibrium. And this is also only the case if the processes are very slow. And I mean very, very slow. If we have a heavy rainfall on a dry soil, water is not distributing in the soil according to some energetic minimum, but it goes where it can easily go to. And this produces also situations where our classical concepts do not really apply. So, well, yeah, this is typically not fulfilled when water infiltrates dry soil. And I have one illustration for you, an experiment in the lab, because this is difficult to observe in real soil. This is infiltration into a rather homogeneous material. I can show it again, where the middle horizon both has low capillary forces because it's coarse textured, and maybe also problems with wettability. This produces this finger-like flow where the soil is circumvented more or less, and rapidly the water is going down to deeper horizons. Okay, so we made quite a lot of advances during the last, let's say, 1 or 2 decades in looking how water behaves in soil at the pore scale. And what you see here is an aggregate, and we look inside these aggregates using X-ray tomography. And you see here the beauty of the pore space, different pore sizes from green, small, to red, large. And we can actually analyze this today in a nicely quantitative way. If it's saturated with water, we can either simulate how it's drying, or rather, or already we can measure it directly with these X-ray systems. And it was already mentioned by Ulrich Schur and Jan van der Borg that these techniques can be used to image the 3D root systems as well. But we are mainly focusing on the soil structure, which is also a structure of pores and solid, which is critical for all the water storage and water movement, and which actually can be changed by agricultural management. This is where we get a handle on how the soils behave in dry situations. Okay, but how is this, what are the implications at the scale of a soil profile? And this was already mentioned by Jan. We have our lysimeter network SoilCan all across the Helmholtz centers. Here again, the map of the different sites. This is really a unique set of data from 140 lysimeters. I think it's, well, anyway, there's a lot of. And we have 13 different soils here, which are moved around from between the different locations and monitored more than 10 years. This gives a huge data set, which is absolutely great to really develop further our models, also under extreme situations. And just to give you a glimpse of the data coming out of that one, here you see water content and water potential as monitored during 1 year, 2013. In the right panel, here you see the precipitation pattern, which was still pretty wet in Germany. In the year 2018, we had from March to September almost zero, just to see the difference. The bad news is that what we typically assume here, this unique curve, is not at all met, but we have a lot of points not lying really on a straight line. But the good news is that there is a pattern in the data which we can understand and which we can use to improve our models towards dynamic wettability, hysteresis, and things like that. And here the green and the red trajectory is the dynamics after heavy rainfall following a dry period. This is what I meant before by that these situations are difficult for our classical model approaches to be coped with. Okay, so what about last 2 slides for the landscape scale? Maybe you have seen the UFZ drought monitor, which is online since quite a while and which shows from day to day the actual situation all across Germany. Here you see the water deficit with respect to percentage of usable field capacity. And this was the situation for 1 week from now for soil profile the first 1.8 meters. And you see these red colors all over the place during the last 3 years. And to come up with such predictions, this needs soil information. And this is still not optimal at the moment. And we are working on how to better characterize the distribution of soils in the landscape. And the approach we are following here is to use data from remote sensing, available soil data, data from parent material of soil formation, different qualities of data which are available in a spatially continuous mode, so-called proxy variables for soil formation. And we combine this with ground truth, where we have real soil data measured at different points. And these two informations are combined by advanced methods of data science, machine learning, and so on, to come up with an estimation, including uncertainties about the distribution of soil properties in the landscape. And this will finally provides us with the required parameter fields to do hydraulic modeling also at the regional scales. So the good point is that these proxy data, especially those from satellites, are steadily improving at the moment. Another good point is that also computing power to do all these calculations is steadily increasing. Well, and the bottleneck at the moment is the availability of the data. And since quite some politicians are here in this group, maybe this could be mentioned that we need better access to soil data, which actually are existing with the different federal agencies, but there is no good access from a scientific point of view. This could be improved. Well, I would like to end just with a statement that many critical issues are yet to be explored, and there are different fields. I think Alon Bengal made a nice list of things where we could collaborate in future. Thanks.
Thank you.